Hey y'all, this lesson is on absolute value equations and inequalities. So we're going to look into solving absolute value equations and inequalities, and then also a little bit into looking at the graphs of those to help us solve them. Before we get into solving, let's talk a little bit about what absolute value is, and that's going to help us as we set up our equations and inequalities. So absolute value is the distance a number is from a given point, maybe 0. And since this indicates that absolute value is always positive because it represents a distance. So if you think about if you're explaining distance to somebody, we talk usually in miles. So when we talk about miles or feet or whatever, yards, we express that in positive values. So we're looking at a positive unit, basically. So let's draw absolute value of x equals 3 on a number line. And what this is saying is that the distance of x from 0 is 3 units. So I'm going to draw what that looks like. It'll just be easier if I draw it rather than try to explain it in words. So my center point is 0, and this is saying absolute value of x. The distance of x from 0 is 3 units. Well, on a number line, you can go in 2 different directions. So you can go 3 units to the right or 3 units to the left. So I'm going to measure that out on here. We can go 1, 2, 3 units to the right. Or we can go 1, 2, 3 units to the left. Both of those represent a distance of 3. So x could have been, let's write down here, -3 or +3. Both of those values represent a distance of 3 from 0. This means that we have 2 possibilities when we're looking at absolute value. If absolute value is just measuring a distance, and we have 2 possibilities of a distance of 3 from 0, then we have to take into consideration that there's a positive possibility and a negative possibility. And this sets up our 2 cases whenever we solve absolute value equations and inequalities. We always have 2 cases, the positive case and the negative case. And when I say the positive case, I usually mean the original case, whatever case is given to us at the beginning of the problem. So I have an example down here of an absolute value equation. It says absolute value of x plus 5 equals 11. So this means that the distance from 5 equaling 11, we could have the case of the original, the positive direction, or we have the case of the negative direction. And so now we need to solve each equation separately. So we're going to subtract 5 and again subtract 5. And that means that my 2 places could be 6 or -16. Both of those values represent a distance of 11. If we plug that into the original equation, we can see plugged in 6, one of our values was 6. 6 plus 5 is 11. And the absolute value of 11 is 11. So that one's good. And then -16 plus 5, we want to know if that equals, whoops, I want to do the original case, sorry. The original equation is the absolute value of -11 equal to 11. And it is. Anytime you take the absolute value of something, you make it positive because it's representing a distance. So both of those check out. And both of those are my representations of that distance. Let's look. Okay, so this was for equations. Anytime you have an equation, basically what you want to do is, in this case, the absolute value was already isolated. Sometimes there might be a number in front of the absolute value. So before you set up your cases, you're going to want to isolate the absolute value. Once you've isolated the absolute value, then you can start setting up your two cases and solving. And then it's always a good idea to go ahead and check your solutions, because there are a few special cases where you're going to get no solution. And so when you plug in your solutions and you see, oh, that didn't work, you want to go back and make sure, did I do something wrong? Or is this one of those special cases? And then that leads into absolute value inequalities, but there's a little bit more to the inequalities. So let's just look at a graph of the absolute value of x. So if I do a table of values to draw my graph, and my equation is y equals absolute value of x, then I'm just taking the absolute value of each x value that I've chosen. So the absolute value of -3 is +3. Absolute value of -2 is +2. Absolute value of -1 is +1. Absolute value of 0 is 0. Absolute value of 1 is 1, and so on. And so basically what we're seeing here is a V-shaped graph. So at -3, my y value is 3. At -2, my y value is 2, 1, 0, and then it goes back up, because basically what's happening is we're seeing the positive representation of x. Now we know that a linear equation would go down this way. And basically all these values are being reflected up into the positive y-axis. And it makes this V-shaped graph. I'm going to draw that really quick. It does keep going forever. My table stops there, but it would keep going. And then down below it says, in the same graph the line y equals 2. So I'm going to use a different color. Y equals 2 is going to be a straight line through 2 on the y-axis. And it looks like that. So I've got two different equations graphed on the same coordinate plane. Where on the graph is the absolute value of x graph greater than y equals 2? So we have this baseline here of y equals 2. Where is the V higher than the baseline, the purple line? It's higher than the line here and here. So if we look at the corresponding x values for those pieces, that is from basically -infinity to 2. It's greater. I guess I'll write that to be more specific. I'll write that absolute value of x is greater than 2 from -infinity to -2. And then it kind of jumps here because that's less than. And the rest of it's up here, which goes from 2 to infinity. So I'm going to do a union 2 to infinity. And union just means that we've got a break in the graph. So we have these two different pieces, this piece, or, which is union, this piece. And then it says, where is it less than 2? So absolute value of x is less than 2. I already kind of mentioned that it's below 2, our baseline, down here in the crook, the vertex, if you will. And that exists from -2 to 2. This graph is lower than the baseline on this interval. So we say -2 to 2. And I did use parentheses instead of brackets because these did not have the equal to sign on it. And basically this is going to lead into how we set up our cases for inequalities. So in the case where we were looking at greater or greater than or equal to, on the previous page, we were just looking at greater than, the relationship mirrors that of an inequality with the word or in it. If you can hear my dog snorting, I'm very sorry. He's silly. And we associated or with the union. That's a U. It looks kind of funny. But the symbol of a union. And then in the case of less than, we're actually relating that to an inequality with the word and in it. And the word and is associated with the intersection. Or if you've watched my video with inequalities, it is kind of like this setup, whereas the or is kind of like this setup. I'm going somewhere. Trust me. Stay with me. So when you set up your two cases to solve absolute value inequalities, you still have two cases. Your first case is your original case. Nothing changes. I will say the only thing that changes is if your absolute value piece is not isolated, you're going to have to isolate it first and then set up your two cases. I think I have an example in here. Yeah, I have a couple examples in here of that so you can see it. And then in the second case, we have to flip the inequality, and we still have to change the sign. So we'll have to do the negative case. And that flipped inequality comes from up here. We had basically, when I wrote it in interval notation, but what's happening is when we had the or case, well, in either case, but we'll just look at the or case, this represents x is less than -2. And this side represents x is greater than +2. So you can kind of see these two cases forming. We have -2 and +2, positive and negative. And then we have the original case and the flipped case. So in the second case, we've changed the sign and we've flipped the inequality. So whenever you're setting up absolute value inequalities, no matter if it's and or, you have your two cases, one positive, one negative, the inequality is flipped. So let's look at some examples so we can figure out what we're doing here. We're solving and graphing these. In number one, the absolute value is already isolated. It's all by itself. So I'm going to go ahead and set up my two cases. My first case is the original case. And then the sign of, or the original inequality is going to decide whether this is and or the word or. Less than ended up being the graph of an intersection. My other dog just walked in, so we'll see how that goes. And it's frozen. Sorry. So less than represented intersection, which represents and. And then our second case, we flip the inequality, change the sign. And now you'll solve both cases separately. We'll add 6, divide by 2, add 6, divide by 2. And we have these two different cases, but it is an intersection. So let's read these real quick. It says x is less, nope, less than, oh, I see. Made a little mistake. This is supposed to be greater than. Got to catch those. It says less than 7 and greater than -1. So let's look at that on a number line. We've got -1's over here, 7's over here, 0, just kind of some reference. It says less than 7. So that's going to go this way. and greater than -1. So that would go this way. Those two arrows are pointing in the same direction. So their intersection is in the middle. And so we would write that parentheses -1 to 7 parentheses. And that's your answer. So all of these values in here, not including -1 and 7, satisfy this inequality. And so you could pick any number in that range, plug it in, and it would be a true statement. And this ties back to the previous page where we looked at the graph, and the place where it was less than that baseline was on this interval, -2 to 2. So you can kind of see some similarities here. Hopefully. If you don't, you will soon. Next one, the absolute value is already isolated. So we can go ahead and set up our cases. We have our original case. And then greater than, if we look back at our graph, greater than represented these two separate pieces here with that break in the middle, which means that we're going to be using the word or. In our second case, we will flip the inequality, change the sign. Got to remember to flip that inequality. And now we'll solve each case. Add 8. Add 8. Divide by 3. And now we have two cases. X is greater than or equal to 5 or less than or equal to a third. Just making sure I solved that correctly because we got a fraction. 8, 1, 5 by 3. Yep. Okay, so if we graph those on the same number line, I'm just going to kind of sketch it here. We've got 1, 2, 3, 4, 5. We have a bracket on a third. Oh, I need to go one more. There we go. Which is like about here. Less than or equal to. And a bracket on 5 greater than or equal to. So there's those two separate pieces like I showed on this page. We had those two separate pieces separated by or. And that sets up on this our two separate pieces separated by or. So you can see hopefully how they're relating. And now we can write our interval notation. This is -infinity to a third included, union 5 to infinity where 5 is included. And that's your answer. Number 3, you are going to want to isolate the absolute value first. So that means we're going to have to subtract 2 and then divide by 3. Now we can set up our two cases. So we have our first case, which is the original. You can always get at least half the problem because you can set up your first case. Greater than or equal to represents those two pieces out on the sides, which is or. And then we are going to flip the inequality, change the sign. So now we add 1, add 1, and then we're going to graph our two pieces. So I'm going to do a straight line, arrows. We'll put -1 on here and 3 on here. You can put more values, it'd probably be a little bit better, but I'm just sketching, so it's okay. We have a bracket on -1 pointing to less than, and a bracket on 3 pointing to greater than. And so now we can write that -infinity to -1 bracket, union, bracket 3 to infinity. And that's it. You're done with that one. We have one more. So go ahead and try this one on your own, pause it, and come back to check your answer. I will say, hopefully you haven't paused it, I will say keep watch, this is a negative. So if you paused it and came back, you should have found that when you isolate the absolute value, you have to divide by -2, which flips the inequality. And so now your two cases are x minus 4 is less than or equal to 2. That's our original. And x minus 4 is greater than or equal to -2. Then we're going to solve each one. Less than or equal to 6 and greater than or equal to 2. Yeah, 2. I do want to say, this is the fourth one, but hopefully by now you've kind of noticed, once you have your absolute value isolated, when you set up your two cases, you'll go ahead and drop the absolute value bars. So you'll see that on all of these. I have this isolated, I dropped the absolute value bars. This was isolated, so I dropped the absolute value bars. So when you go set up your two cases and you want to go solve, you can drop those bars and just solve them like normal. So now I'm going to graph these on the same number line. We've got, goes from 2 to 6. We have greater than or equal to 2. So that goes this way. Less than or equal to 6. That goes this way. Our two arrows are pointing towards each other. So we're going to shade all in between, which means that all the values in between 2 and 6, including 2 and 6, satisfy the original inequality. Okay, next page, last page for this lesson. I have an example similar to the one that I did before we started the previous page. I have graphed two equations on the same coordinate plane. One of them represents the absolute value of 3 minus x, and one of them represents y equals 2. And so you can kind of see the red one is y equals 2, and the v is obviously the absolute value. So without using algebra, without solving algebraically, I'll say, solve this by looking at the graph. So just seeing this piece solve these inequalities. Go ahead and try it on your own, pause it and come back and then check your answer. You should have found that the absolute value, which is the v, is less than this baseline here. So it's below, it's less than the baseline here, which represents the intervals, looks like from 1 to 4. And so that's going to be 1 to 4. I did use parentheses because this was just less than. It didn't have the equal to. And then for the next one, it's wanting to know where it's greater than or equal to 2. And so you're looking to see where the absolute value graph is higher than the line of 2, y equals 2. And that's here, these two little arms, which is represented by -infinity to 1, and then there's a break, 4 to infinity. I am seeing a correction here. I'm so sorry. You probably noticed this. This was a 5. I counted wrong. So I'm very sorry about that. That's a 5. The concept remains the same, but that is all I have for this lesson. So if you have any questions, let me know and I would be happy to help. See you all in the next one.